All right, so now's a good time to go ahead and go over this problem that we didn't get around to going all the way through in class. This is in lecture 2a at the very end. So initially we have a runner that's running due east towards the flagpole, and they're starting off at 4 kilometers to the west of that flagpole. At the same moment, there's a second runner, runner B, that's passing a sign that is 3 kilometers to the east of that same flagpole, while running west with a constant velocity of 5 kilometers per hour. How far are the runners from the flagpole when they meet? Now, first of all, let me skip forward a little bit, and a picture is worth 1,000 words, so let's see if we can get the drawing of this problem up. So we have runner A to the west, 4 kilometers to the west, right, towards the west of the flagpole, running at 6 kilometers per hour towards the flagpole. Runner B, Bob, is 3 kilometers to the east and running also towards the flagpole. Okay, we're looking for a position where they will meet. Right. So let's go back now and consider the strategy. I won't talk about this too much because we talked about it in class. This really is a compare two systems type of problem. Sorry, I'm going to flip back here because we know the condition initially. We know where the runners are. We know what their speeds are, right? And what we want to do is we want to look at this same system at some later time where this guy has now moved over to here and this guy has moved over to somewhere in here, right? And the idea is they're now going to be at the same point in space and time, by definition, meeting. So we want to know how the system has evolved from this initial condition to the final condition where they are now at the same place. Okay, so that's why that's a kind of a before and after or a compare to systems type of problem. Okay, so when we're going to do these types of problems, we want to look for the things that are going to stay the same. Whether something is either something's conserved, it stays the same, or it has to be the same as a condition of the problem. Right. So what stays the same in this problem? We know the speed of each runner stays the same because it's stated that they're running at constant velocity. By the definition of them meeting, they have to end up at the same place, and they have to end up at that same place at the same time. So the final positions of both runners must be the same, and the duration, the time spent running, must be the same between the initial condition and the final condition. Okay, so to start the solution, the first thing we have to do in any problem is to be explicit about what we're trying to solve. What is our goal? Right? Our goal here is that we are looking for the positions of the runners when they meet. Right? So we're looking for a position or a displacement. Next thing to look at is what tools do we have, right? We want to be explicit about what things we are given. We're given starting positions, starting velocities, and we look for any equations that would be relevant, meaning that they help us work with these given things and help us reach our goal, which is a position. Right? So we're going to be looking for something that relates positions, displacements, and time. Right? And right now, at the time that we gave this lecture, the only thing we had really worked with was the definition of velocities and average velocity and acceleration. Right? I don't even know if we've gotten to acceleration quite yet. So again, here's the sketch of the problem. Whenever we sketch a problem, we need to define our axes. So we're going to set positive x to be in this rightward going direction, in this case east, the easterly direction. And we have to set an origin. So we're going to choose, this is not the only choice that we could make for solving this problem, but it's a convenient one. We're going to set the flagpole to be at x equal to 0. Right? In that case, what we're looking for is delta xa, how far the runner A had to go before he reached the meeting point, which is not necessarily at the flagpole. Right? The other thing we're looking for is how far runner Bob had to run from his starting point in order to get to the meeting point, which again is not necessarily the flagpole. Okay, so we've decided on a coordinate system. We've written down all our known quantities. I'm going to set the x-axis to run east-west and have x pointing to the east. We set the origin at the flagpole. We then write down are quantities that we've kind of said out loud at this point. The initial position of runner A is 4 kilometers to the west, which, because positive x is pointing to the east, that's a minus 4 kilometers, as you can see from the figure here, right? So this will be in the negative direction, so he's at minus 4 to start with. Runner B will be at plus 3, obviously. Right, so going back forward, runner B starts off, his initial position is plus 3 kilometers. The velocity of Allison, runner A, is plus 6 kilometers per hour because she's running towards the positive direction, east. Runner B, on the other hand, is running to the flagpole from the east, and so that is a minus 5 kilometers per hour. Okay. Now we have all our givens. We have a drawing. We're going to write down the appropriate tools that will help us reach our goal. In this case, those tools are equations that include displacement because that is what we are trying to solve. Right? Our definition of the average velocity is displacement over duration, right? Change in x over change in time. So we could use this for each runner. The velocity for runner A is by definition how far they've run. The average velocity for A is how far they've run divided by how long it took them to run that distance, right? Being a little bit more explicit, we'll break up delta x into final minus initial, right? So that's Allison's starting final position minus Allison's starting position divided by the time it took her to move between those two positions. We'll do, of course, the same thing for runner B. So this is the velocity for Bob using this definition. Okay, earlier, by logic, we concluded that the durations and the final positions of the runners have to be the same if they are going to end up at the same place in time to meet. So we'll write that in terms of equations. That tells us that the duration for runner A, delta TA, and the duration for runner B are the same, in which case we can drop the subscript and just call that delta T, because it's the same delta T for both of them. The fact that they meet at the same place means that the final position for A and the final position for runner B have to be the same. And so again, we will drop the A and B subscript and we'll just call that the final position for both of them. That simplifies our two equations above because we can drop the subscripts and we can say some of these things are equal. We can just say VA is just final position, the one and only final position, minus the starting position for A divided by the one and only duration. And similarly for B, it's X final minus X initial for runner B divided by duration. All right, so we're going to keep that set of equations. Now remember, the goal is to determine the final position, XF. So what we can do is we can rewrite our velocity equations to solve for XF. Right? We have XF here, we have velocity, but right now it's written in terms of we're solving for VA, and if you write the equation down this way. So let's just take either one of these equations, actually we'll take both, and we'll rearrange them. Right? We'll bring the XF over to this side, and we'll bring the VA over to this side. Okay, so let's see how we do that. Well, first thing is we can't just bring this over because it's inside of parentheses. So what we're going to do is we will multiply both sides by delta t, VA delta t, and this becomes just XF minus XAI. So if I then just add XAI to both sides, I'll end up with VA times the delta t what I brought over, plus XAI, and that's what we have here. And I didn't show all the steps because we already have enough steps here, but I encourage you, if you couldn't quite follow that just by listening to me, to write it out for yourself. It's about 2 steps or 3 steps of algebra if you write it out. Okay, XS, the same thing we do for the second equation for runner B, XF is equal to VB times delta T over the initial position for Bob. So then for either of the runner's equations, we are given the runner's velocity, right? We know the velocity and we know the initial position. So we just need the duration. And if we had the duration, then we could solve for xf. But we weren't given duration, right? We could use this equation to solve for the one thing that we want if only we had delta t. So this is now a two-step problem. Our new goal is that we're going to try and solve for delta t. All right, so we have a new goal. Our goal is to find the duration of the run before they meet. Notice we have two equations with two unknowns, right? In this equation, we know the initial, the one and only velocity for runner A, and we know its starting position. We also know from this equation the runner's velocity for runner B and their initial starting position, but in both equations we do not know the final position. That's what we're trying to solve, and we don't know delta t, which is our intermediate goal to try and solve. So we have two equations with two unknowns, and if you'll recall from your algebra, that's a solvable system, right? And one way to solve a system of two equations with two unknowns is to substitute one equation into the other, right? So we have them both written in terms of xf is equal to something, so we can just set them equal to each other, right? We can set the two equations equal to each other, and then that will allow us to solve for the now one and only unknown, right? Because now we have this equation that has only delta t as the unknown. So let's bring delta t to on the same side. So I collect the terms of the delta t's, right? Bring the xa and xbi over to this side by themselves. Factor out the delta t, and then if we divide both sides by va minus vb, we end up with an equation for delta t. Now at this point, it may be useful to go ahead and generally I like to keep things in terms of symbols, but for simplicity's sake, let's plug in some numbers and get a number for what delta t is. Right? So we plug in the known values for the starting positions and for the velocities of the two runners. Plug in, we don't even need a calculator for this, 3 minus minus 4 is 7, 6 minus minus 5. Remember, you have to keep track of the minus signs because of the different directions that they're running and the different starting positions relative to what we call the origin, which is the flagpole. So that's 7 kilometers divided by 11 kilometers per hour, which gives us a final answer of 0.6363. Right? We'll keep a few extra significant figures so we don't end up with rounding errors by the very end. Okay, so it takes about 2/3 of an hour for these two runners to reach the same starting point, or meeting point, the same meeting point. What that meeting point is still unknown, but now that we have delta t, we can finally solve either of these equations because now we have only one unknown. So one equation with one unknown is easy to solve. We just plug in. X final is equal to VA times delta t, the velocity times the duration plus the initial starting position. So that's now 6 kilometers per hour times 0.63 hours. And then we have to add the negative starting position. Right? So that means that the final position relative to the origin, which is the flagpole, is minus 0.18 kilometers. So the runners end up meeting 0.18 kilometers to the west of the flagpole after running 0.64 hours. Okay, it's to the west because xf is negative and we had positive x pointing to the east. Right, you can also plug in the time into this equation and you should get the same answer. And it might be worth it for those of you at home to go ahead and do that. Notice that we've kept the excessive significant figures. We know that we only end up with, our final answer is only going to be at 2 sig figs, but we go ahead and keep 2 or 3 extra sig figs so that we don't accidentally, if we round everything down to 2 sig figs and then we add 2 numbers together, we could have accumulative rounding errors so that you end up by the time you get your final answer, you may be off by that last sig fig. So it's always a good policy to keep, I'd say, 2 sig figs, maybe 3 sig figs, depending on how complicated the calculation is going to be, 2 to 3 sig figs beyond what you are expecting to report as your answer in all your intermediate results. And then finally, once you have a full result, you can trim it down to those last 2 sig figs. All right, and that is the end of that problem.